The title of my presentation is Effect of Normal and Tangential Acceleration on Longitudinal Fracture.
Sorry, Victor, to interrupt you. Please tell us when you want us to go to the next slide, okay?
Yes, thank you very much.
Thank you.
Fracture of inhomogeneous structure rotating around a horizontal axis. Please go to the next slide. Thank you. The need of carrying out of this study is caused by the quickly increasing application of continuously inhomogeneous structural materials for manufacturing of various components of structures and various mechanisms which are involved in different motions with acceleration. In particular, this study analyzes the effects of normal and tangential acceleration on longitudinal fracture in a rotating structure. The latter has a horizontal and a vertical member made by a material that is continuously inhomogeneous along the length of the structure. The material has non-linear viscoelastic behavior. Due to inhomogeneity, the mechanical properties and the material density vary continuously along the length of the structure. The vertical member of the structure is rigidly connected to a horizontal axis around which the structure executes rotation. Since the rotation is non-uniform, both normal and tangential accelerations are induced. The intensities of the distributed inertial loads in the structure due to the normal and tangential accelerations are derived. There is a longitudinal crack in the horizontal member of the structure. The strain energy release rate in the structure under the distributed inertial loads is determined. The influence of the normal and tangential acceleration on the strain energy release rate is investigated. The effects of various parameters of the model are studied. The structure depicted in figure 1 has a horizontal and a vertical member denoted by L1 and L1, L3 and L3, L4 respectively. This structure rotates around a motionless horizontal axis N1. The law of this rotation is given in equation number 1. In this equation, phi is the angle of rotation, t is the time, theta and delta are parameters. The angular velocity of the structure is obtained by equation number 2. Equation number 3 is applied for deriving the angular acceleration of the structure. The angular velocity and the angular acceleration of the structure are shown around the axis N1. The normal and tangential accelerations of an arbitrary point D of the structure horizontal member are found by using equations number 4 and 5 respectively. In these equations, L1 is the length of the member, L3, L4 of the structure. The accelerations AD n and AD tau are shown in figure 1 of the structure. The accelerations of an arbitrary point H of the vertical member of the structure are found by using equations number 6 and 7. Yes, thank you. The intensities of the distributed inertia loads induced by the accelerations are found by applying equations number 8, 9, 10, and 11. In these equations, m is the mass per unit length of the structure. This quantity, m, changes continuously along the structure length due to the continuous material inhomogeneity. Equation number 12 is used for describing the change of m along the length. In these equations, mL1 and mL4 are the mass per unit length in points L1 and L4 of the structure. X is the longitudinal axis. Lambda m is a parameter. The structure under the inertia loads, which intensities are given in equations from number 8 to number 11, has non-linear viscoelastic behavior. The latter is treated by using the model depicted in figure number 2 on your screen. The dashpot of this model has linear viscoelastic behavior that obeys the law given in equation number 14. In this equation, sigma eta is the stress in the dashpot, eta is the coefficient of viscosity, epsilon eta dot is the time derivative of the strain in the dashpot. The behavior of the spring of the viscoelastic model is nonlinear elastic. The nonlinear stress-strain relation in equation number 15 is applied for treating the spring behavior. In equation number 15, sigma r and epsilon r are the stress and strain in the spring. The coefficient of viscosity and other material properties change along the length according to the laws given in equations number 16, 17, and 18. The viscoelastic model that is in figure 2 is subjected to stress sigma written in equation number 20. In this equation, beta and psi are parameters. After performing of some mathematical transformations, the strain epsilon r is extracted from equation number 24, and the result is given in equation number 25. The strain in the viscoelastic model is obtained by applying equation number 27. By taking into account equation number 19, we transform equation number 27 in equation number 28. This equation then is used as a stress-strain time relation for treating the nonlinear viscoelastic behavior of the rotating structure. The longitudinal crack in portion L1, L2 of the horizontal member of the structure has length A, the strain energy release rate is derived by applying equation number 29. In this equation, U asterisk is the complementary strain energy accumulated in the structure. B is the width of the structural member. The complementary strain energy is found by integrating of the complementary strain energy density in the volume of the structural members. The complementary strain energy density in an arbitrary point of the structure is derived by using equation number 30. In this equation, sigma is expressed as a function of epsilon by applying equation number 29. The rotating structure is subjected to bending around both centric axes y and z by the distributed inertial loads induced by the normal and tangential accelerations. Therefore, the distribution of the strain in a cross-section of the structural member is presented by equation number 31. Here, epsilon c is the strain in the cross-section center. K, y, and K, z are the curvatures in the planes x, y, and x, z, respectively. Y and z are the horizontal and vertical centric axes of this cross-section. Then equations number 34, 35, and 36 are used to determine the strain in the cross-section center and in the two curvatures. In this equation, A is the cross-section area, N is the axial force, M, Y, and Mz are the bending moments generated by the distributed inertial loads. Finally, the strain energy release rate found by equation number 29 is confirmed by solution given in equation number 37. Further, we analyze the effect of various parameters of the model of the structure rotating around motionless horizontal axis on the longitudinal fracture. In this relation, the solution of the strain energy release rate is applied. The effects of the length of the vertical member of the structure and the variation of the material properties along the length of the structure on the longitudinal fracture are studied first. The length of the vertical member and the variation of material property R are characterized by L1 to L2 and RL4 to RL1 ratios. Figure number 3 gives an idea about the change of the strain energy release rate induced by increase of L1 to L2 ratio at different RL4 to RL1 ratios. The quick rise of the strain energy release rate.
You have 1 minute left. Sorry to interrupt you.
Yes,
Okay.
I am near the end.
Yeah, thank you.
The quick rise of the strain energy release rate can be explained by increase of the normal and tangential acceleration. The reduction of the strain energy release rate with growth of RL4 to RL1 ratio is a consequence of increase of the structure stiffness. On the next figure, figure number 4, the influence of parameter theta and the variation of material property eta are analyzed, and the results are illustrated by the graphs in figure number 4. Finally, the effective parameter theta and the distribution of mass density are studied, and the results are presented in figure number 5. Next slide, please. Figure number 5. So finally, it can be recapitulated that the theoretical study of longitudinal fracture in continuously inhomogeneous nonlinear viscoelastic structure with two members rotating around a motionless axis is performed. The study indicates that increasing of L1 to L2 ratio causes a quick growth of the strain energy release rate. Increasing of RL4 to RL1 ratio induces a reduction of the strain energy release rate. The strain energy release rate reduces also when eta L4 to eta L1 ratio grows. And also growth of ML4 to ML1 ratio leads to increase of the strain energy release rate. Thank you for your attention.